Hello, everybody. I am Quang from the Graduate School of Data Science, presenting on behalf of my teammates Dongkyun from the School of EE and Sumin from the School of Computing. Our project's title is Continual Learning of Critics. So imagine that you have a problem. If it is simple enough, the first thought that you come up with may already help you resolve the problem. But problems in reality are often more complicated. So the process typically looks like this. You come up with a solution. Then you reflect on it, point out mistakes, and then correct yourself. This process is repeated for some times until finally you obtain a good solution. This is what we call critical thinking, and it is an important factor of the human learning process. Employing this intuition, a number of previous works have examined the use of different supervised or reinforcement learning frameworks to create critics. These critics are typically developed to specialize in particular tasks, such as summarization or math word problems. However, as humans, we learn to criticize and correct ourselves on various tasks during our lifetime with the same hardware that is our brain. When you learn to self correct yourself while doing calculus, for example, you don't lose the ability to be critical while playing chess or to correct your posture while walking. So, this naturally leads us to a question. Can artificial critics continually learn just like their human counterparts? As such, in this project, we make the first step towards an answer by an evaluation of how our critic models stand against a continual learning setting. Despite there being many relevant algorithms, we consider only one of them, RL4F, due to compute budget. At a high level, we have an input X and a previous attempt at solving the task Y hat. The critic model, in our case, T5 large, receives these two items and produces a critic C. All of these are then fed into a task model, in our case GPT 3.5 Turbo Instruct, to produce a new attempt. And the discrepancy between this new answer and the ground truth serves as the reward signal for the critic to update with PPO. Note that here only the critic is fine-tuned. We leave unchanged the task model, which is typically a large language model that is expensive to update. In order to describe our continual learning setup, we now introduce the tasks. We have three tasks in natural language, drawing also from R4F. The first one is called interscript, which is action planning. The second task is summarization. Both of these are evaluated through BERT score for semantic similarity and ROC for lexical similarity. Finally, we have alphabetization, which is a word sorting task. It is evaluated through exact order match and inverse Levenshtein distance. So with these tasks, we fine-tune the critic through two tasks sequentially and evaluate the task performance before any training, after training on the first task, and after training on the second task. So the results are overall quite positive. We can observe knowledge transfer, that is, training on one task might benefit the performance on another. For example, in the first column, which contains results for the sequence of alphabetization and interscript, we can see how learning the alphabetization task actually increases performance in terms of the BERT score for interscript. Note that even though ROC score for in this case decreases actually after alphabetization is learned, we would argue that semantic similarity measures like BERT score matter much more than lexical measures like ROC for interscript. Additionally, there is also minimal forgetting of previous tasks across all evaluated sequences. For example, you can look at the last column for the sequence of summarization and then interscript. In the third row, that is the BERT score for summarization, you can see that training on interscript does not really affect the previously learned critiquing skills for summarization. So our takeaway is that the algorithm that we consider seem to be quite good for continual learning. But there's still a lot of exciting questions regarding critics that deserve further investigation. They involve the assessment of critic models in longer test sequences and also in more domains, the design of good critic algorithms, and perhaps most importantly, whether critic models are actually necessary for reasoning. As part of our investigation in other domains, we have created a synthetic critic dataset for mathematics problem solving. More details will be in our report. If there is any need for correspondence, please contact me at the email shown here. Thank you.